So this example of finding the zeros of a polynomial function and using them to graph is a little bit easier for us because they've already factored this one for us, right? What we're going to focus on here now is how the leading coefficient test changes and how identifying multiplicity of zeros is actually a little bit easier. Okay. Now, in terms of the leading coefficient test, when you first look at this, if you only look at the exponents, because this is already in factored form, if you look at this and you say, oh, this is a third degree polynomial, that's not necessarily true. Okay. Because this is in its simplest factored form. Really, what this looks like is, if I may, write x as x minus 0 cubed, and then we have x minus 2 squared, and then we have x plus 4. And what is that? That's really x minus 2 times x minus 2 times x plus 4 times x times x times x. So if I expanded all of this, and even if I just expanded these last two, okay, I would end up with a third degree value of x with a bunch of other stuff, right? And that x, when this becomes x squared at some point through this expansion and gets multiplied by this, that's where the x cubed comes in. Notice that the leading coefficient is 1, okay? Now if I take this and I multiply it times this x cubed, that's really x to the 6th, blah, 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 blah. So when we talk about the leading coefficient test, we only care about the highest exponent of x, but we need to know what its degree is, right? So don't just view this as, oh, it's x cubed. Actually, it's x to the 6th if we went through expanding this entire expression. So that makes this an even degree polynomial. And we still want to look at the leading coefficient, which is positive. So we know that the end behavior is rising to the left and rising to the right. As far as the x-intercepts are concerned, this is where our work has been made easier for us. We see all of these linear factors with coefficients of x that are 1. So we know that our x-intercepts are 0, 2, and -4, right? Remember, we're using the opposite of the numbers that show up in these linear factors. So here are our zeros, okay? In terms of which zeros cross the x-axis, these are zeros with odd multiplicity. And when we talk about multiplicity, we're talking about odd exponents for the factors, okay? So this is where we come back and we say, well, this factor of 0 happens 3 times. That's an odd multiplicity. So we know that this is what we call a bounce, or they're calling it I'm sorry, this is a cross, not a bounce. So this is odd multiplicity, right? So we know that this is a cross. Anything with an even multiplicity, like we see here, where the exponent is a 2. So for this 0, we know this is a bounce, okay? And for the -4, the exponent of that factor is 1, so we know this is also crossing, okay? So where does it cross? At 0 and -4, because their linear factors have an odd exponent. And then we know there's a bounce for 2 because there is an even exponent. The y-intercept, when we plug in 0 for all of these values of x, okay? And then we've got 0 plus 4 here at the end. 0 cubed is 0. What do we get here? Doesn't matter, right? Because we're multiplying this term becomes a 0, and 0 is getting multiplied by this, right? So it doesn't even matter. Yes, this ends up being -2 squared, and yes, this ends up being 4, but we're multiplying all of that by 0. So it doesn't even matter. We know our y-intercept is 0. The symmetry of the graph, okay? This is where things get a little weird and might require a little bit of effort. But I know I'm going to have an x to the 6th term, right? So I know that it's definitely not odd, okay? I know right now it's not odd. I know that its symmetry is not about the origin, right? That is an odd function that has symmetry about the origin. I don't have that here. The question is it even? But remember that even functions can only have even exponents, right? And we said throughout this whole thing, if I expanded this entire thing, okay, this entire expression, we may have to do a little bit of work with that. Now, we could bypass it a little bit with a test here or there, but one thing we'd want to do is we'd have x cubed, right? We'd have x squared minus 4x plus 4, and then we'd have x plus 4, right? So this is the first expansion of that entire expression right here. Now let's just go very quickly and expand this. We'd have x cubed plus 4x squared minus 4x squared plus 4x plus 16. Okay, if I do this times that, and this times that, and this times that, and this times that. Oh, I forgot my 16x. My bad. Plus 4x plus 16. What do we end up with? We've got our x to the cube still on the outside. We've got x cubed on the inside. Our x squareds cancel. We've got 20x here, and then we've got plus 16. What happens when I multiply by x cubed into all of this, right? This x cubed that was hanging out on the outside this whole time. X to the 6th plus 20x to the 4th plus, oh, we almost made it. We almost made it, right? We got to the very last term, and in this very last term, I had 16x cubed. That's an odd degree value of x. Because it's an odd degree value of x, it can't be even. Remember, even functions only have even exponents of x. Okay? And because I ended up with one odd term at the very end, all right, it's not even. So it's not odd and it's not even. All right? Last but not least, let's go through this. We had a 0 at 0. We had a 0 at -4. We had a 0 at +2. We know that there's a bounce at +2. And we know that it has left and right end behavior like so. We cross at -4. We cross at 0. We come back down. We're going to get something like this. Who knows how high it goes? Who knows how low it goes? But it has to come back up and cross, then it has to come back down and bounce.